Right, hello. Today we're going to prove that if we differentiate x to the n with respect to x, we will get n multiplied by x to the n minus 1. So you drop the power and bring the old power to the front. We'll do that with first principles. So let's first of all write out the formula for that. So first principles. And that states that if we have any function f that is going to be a function of x, and we differentiate it with respect to x, what we end up with is taking the limit as dx tends to 0 of f evaluated at x plus dx minus f of x. So the difference in the y's is how you can think of it, and then the difference in x is on the bottom. So this is basically the gradient function, but as the gap between the 2 points becomes really small. We're also going to need the n choose r formula, n choose r, and that is equal to n factorial divided by r factorial multiplied by n minus r factorial, like that. Beautiful. So first step then, let's write out our, instead of f, we have x to the n. So d dx of x to the n is equal to the limit as dx tends to 0 of this big function here. So our function was x to the n, but we're now evaluating at x plus dx, so it's x plus dx to the power of n. And we take away then the original function, x to the n, and divide that whole thing by dx. Beautiful. First step then, we're going to expand this using the binomial expansion formula. So let's write out our limit first, dx goes to 0. And this then can be written as the sum from r equals 0 up to n of n choose r, multiplied by x to the n, and then multiplied by dx to the n minus r, like that. Take away the x to the n, it's still on the end there. Beautiful. dx. What I'm going to do now then, after writing in the limit, always remember to write your limit in, is we're going to have a look at some of the terms in here. And we're going to look at like the last two terms, so the terms when r equals n and when r equals n minus 1. So when r equals to n, we'll have n choose n, x to the n, dx to the n minus n, but that's just 0. If r was n minus 1, we'll have n choose n minus 1, x to the n minus 1, dx to the 1, like that. Beautiful. And we can still write the summation in here. What we're going to have is this is exactly the same now, except instead of going to n, it goes to n minus 2, as we've taken off the last two values. So n choose r, x to the r, dx to the n minus r. We'll wrap that in a bracket just to make sure we don't include the minus x to the n in our summation. Put that whole thing on the numerator, and dx remains in the denominator. Beautiful. So let's try and simplify these two terms we brought out the front. We still have the limit as dx tends to 0. And let's evaluate these terms then. So if we have n choose n, let's have a look at what that should be in terms of our formula. We'll put it up here. So n choose n would be equal to n factorial divided by n factorial. So those two are going to cancel out straight away. And then n minus n factorial, so that's 0 factorial. So that cancels out to be 1, that's also 1, so that whole thing equals 1. We'll have a look at the next term then, so n choose n minus 1, and what we get is n factorial divided by, well, it's going to be n minus 1 factorial over 1 factorial. The 1 factorial is just 1, so we can ignore that as well. And n factorial, if we remember that that is written as, well, can be rewritten as n times n minus 1 factorial over n minus 1 factorial. We can see that these two are going to cancel off, and we're left with just an n at the end. So beautiful, let's plug those into our big bit over here. So that's going to be, at the start was just 1. So we can ignore that and have x to the n. And remembering that dx to the 0, that's going to be 1 as well. So we don't need to write anything else in there, that's the entire term. Next term then, we have n, x to the n minus 1. So that looks very nice in what we want as our target. Very, very nice indeed. And dx to the power of 1, so we'll leave off the power there. We then have our nice summation here, and we'll leave that there for a second. Summation from r equals 0 to n minus 2 of n choose r, x to the r, dx to the n minus r. And this whole thing then, we take away x to the n. Denominator is still dx. Very nice. So what we can see straight away is these two terms, this minus x to the n and positive x to the n, they add together to make 0, so we can ignore both of those, which is very nice. So going on to the next line, we still have our limit as dx tends to 0, n x to the n minus 1 multiplied by dx. And we're going to have a look at the summation now and just think about each term step by step. And we're going to look and see, does each term contain a dx? Because we want to see, is it going to cancel off? So does each term contain a dx? And if so, what power of dx does it contain? If we look at r equals 0, we'll have n minus 0. So that definitely contains dx. It contains dx to the power of n. If we look at the other end, n minus 2, we do dx to the power of n minus 2. So the n's will cancel, and the minus 2 will become a positive 2. So we can effectively take out a dx squared from this, and then drop the power by 2 in there. So r equals 0, n minus 2, and choose r, x to the r, dx to the n minus r minus 2. Very nice. And the whole reason we've done that is, what we want to do now is we want to stop this from being a fraction, and we're going to divide everything on the top row, everything in the numerator, by our denominator of dx. So let's go to the next line, limit dx tends to 0. And let's actually do the division. So we're going to have n x to the n minus 1, and the dx's have cancelled, plus dx, which is dx squared divided by dx, lots of our summation. So from sum of r equals 0 to n minus 2 of n, choose r, x to the r, dx to the n minus r minus 2. Beautiful. So now we can start to evaluate our limit. And what we're going to be able to see is that this very horrible looking summation, close the brackets up there, this horrible looking summation is always going to be multiplied by 0. Doesn't matter what term we're talking about, they're all multiplied by 0. So the entire thing evaluates by 0, evaluates to 0. So when we actually evaluate this thing out, all that we're left with is this first term here, which doesn't contain the dx, so it just comes out by itself, and that's n, x to the n minus 1. And that is it. We've proved exactly what we wanted to prove. Beautiful.